Welcome. I'm here to talk a little bit about the basics of logarithmic functions. I'm not trying to replace the teaching of that unit in your Algebra 2 class, your pre-calc class. I'm just looking to give you a little bit of basic background on them. From my take, I teach a calculus course, and my students are at that point right now. We're getting ready to do the derivatives of transcendental functions, ln and e. So I wanted to give them make sure they remembered a little bit of the basic background on logs so that we can actually do the differentiation and understand what we're doing and when to apply things such as the log properties and such. Bottom line is, I think before we talk about a logarithmic function, it makes sense to talk about an exponential function, which is basically a function of the form f of x or y equals b to the power x, b representing your base and x some unknown exponent. If you say, well, I thought this video was about logarithms, why do I want to talk about exponentials? Well, basically because a logarithm is the inverse of an exponential function. And as such, there's a certain relationship that it has to the exponential function, which we'll talk about later in the video here. But if you go Google the definition, you'll probably see something about a logarithm being a quantity representing the power to which a fixed number must be raised to produce a given number. Bottom line, people, a logarithm is an exponent. When I see a function and I see a log in it, I'm basically looking, okay, what power do I need in order to raise some base to that'll give me a certain value? That's the basic idea behind a logarithm. Is what power does this represent? What power is needed? That's kind of what goes through my head when I see these expressions. Couple of forms to be aware of. Exponential form, we just talked about the equation of an exponential, y or f of x equals b to the power x. To take that same equation and write it in log form, or to convert it to log form, I would write it as log base b, again because the base in my exponential is b, the base of my log is also b, of some number y equals x. In other words, when we talk about an exponential, we're talking about some unknown power x. So when I'm doing a log, I'm saying, what power does the base b need to become y? And that power is x. Some basic log information. So if you're wondering who to hate for creating these things because it's driving you bug nuts in your algebra class, these two guys, John Napier, Just Berge, came up with these in the early 1600s, working independently from each other, and actually had a couple of different, their takes on them were a little bit different. In addition, their works, what they accomplished back then, are different from the common logs, which are base 10 logs, and natural logs that we use today. If you wonder why did they do them, why did they even think of contemplating or coming up with these? Basically, they wanted to create a means of simplifying some really harsh mathematical computations and calculations. So that's kind of the genesis of where they came from. I'm pretty sure most of you know what 10 is for like our base 10 log. If e is something you're not quite as familiar with, let me give you a little background on e. E is approximately 2.71828182459045, and well, on and on and on again. It's irrational. Much like pi, approximately 3.1415926 and on and change, something like that, is an irrational number. Both have applications in mathematics and in the real world. I'm not going to go into that in the video, but I don't know if it helps for you to think of it this way. Pi is an irrational number slightly larger than 3. E is an irrational number slightly smaller than 3. If it kind of helps you to understand like their relation, their magnitudes, things like that, if it helps, go for it. Okay, before we get into like the algebra behind it, I think I'd like to talk about the graphical perspective of it. I'm big into multiple representations, so let's throw in some equations, tables, graphs. We'll have a good time. I'm going to start with the easier of the two, coming up with a table for the exponential function y equals 2 to the x. I just picked some random numbers here. Actually, they weren't really random. I picked a few positive numbers, a few negative numbers, and 0 for my values of x, my independent quantity, and then use those to find my dependent quantity, y. If the table's confusing to you, you're saying, where did these numbers come from? Well, let's start with 0. Again, x is my exponent, so if I take 2 to the power 0, I get 1. If you're wondering why 2 to the 0 is 1, maybe you've heard your teacher talk about that any number to the power 0 is 1. Hopefully they did not include 0. 0 to the power 0 is undefined, but other than that, you're probably pretty safe to say that a number to the power 0 is 1. When you choose the x value of 1, 2 to the 1 is 2. 2 squared gives you 4. 2 cubed gives you 8. Those are pretty basic. Now your negative exponents maybe cause you a few fits here. We'll deal with those. So at negative 1, what we're basically saying is, if I take 2 to the power negative 1, what do I get? Well, the answer is 1/2. If you're wondering where does the 1/2 come from, the idea is basically this. When you take something and raise it to a negative power, specifically the negative 1 power, what it does is make its reciprocal. So the reciprocal of 2 is 1/2. When you raise something to the negative 2 power, it basically takes the reciprocal, so the 2 becomes the 1/2, and then you square it, and you get 1/4. Likewise, when I raise it to the power negative 3, the negative turns the 2 into a 1/2, and then I cube it, thus giving me 1/8. Now, if you recall previously, we talked about exponentials and logs being inverses. That's what comes into play here with our table. So I have a table of y equals 2 to the x that we just talked about. So if I want a table of y equals log base 2 of x, its inverse, you might recall that inverses occur when f of g of x equals x. That's another story for another time. But when you switch the domain, the x value with the range y values. So if I can come up with the table for my exponential, all I have to do is switch x and y. I have the table for my log function, its inverse. And from there, I wanted to show you a graphical perspective so you can kind of see what you're dealing with. Again, my y equals 2 to the x. As I go out here in the negative direction, my y value is getting very, very small, pretty close to 0, and getting bigger, and then they just take off after a certain point and get just ridiculously huge at a certain point. Here is its reflection across the linear parent function y equals x. That's our logarithmic function, and again, from your algebra class, you probably talked about that inverses are reflected across the line y equals x. So a little graphical take on that idea. Let's play with a few examples of logs and how to evaluate them. None of these are really too difficult, but they're important to help you kind of understand the concept. I'm going to start here first with log base 2 to the 16. Again, remembering that a log represents an exponent or some power you're looking for, some unknown power. So when I read this, log base 2 16, I'm thinking, okay, not what is 2 to the 16, which is some insanely huge number. I'm thinking of, if I have a base of 2, what power do I need to raise it to get 16? And the answer is 4. Log base 2 of 16 is 4. Because 2 to the 4 is 16. Over here, what we talked about in the table before might come in a little handy here. If I have an expression, a logarithmic expression, log with a base of 9 of 1 to the 9 is something. You say, well, how do you turn 9 into 1 over 9? Well, 1 over 9 is the reciprocal of 9, and as we talked about before, if you want to take something and make its reciprocal, that power is -1. Next one, log base 64 of 8. If you say, how do I turn a 64 into an 8, and how does that work from like an exponent perspective, since a log is basically representing of an exponent? The answer to that logarithmic expression is that log base 64 of 8 is 1/2. If that's not working for you, maybe this will help. The 1/2 power is basically the same idea as taking the square root. So if I take the square root of 64, I get 8, which means that 64 to the power half gives me 8 because that's the square root. A couple that are really good for calculus, you'll probably want to know these. ln of 1. Well, again, that kind of ties back to the table. You say, okay, what does this represent? Well, ln means I have a log with a base of that Euler's number. So ln of 1 means I have a log base e of 1, which means what power does e need in order to become 1? And we talked about that. What power do we need to make 1? Well, that power would be 0. So ln of 1 is 0. Another thing that could come in handy here is knowing what the natural log of e is. Again, from perspective, ln means log with a base of Euler's number. So when I see ln of e, it basically means what power does this base e need in order to, well, stay the same as it was before. And if you know that that's 1, thank an algebra teacher. They did a good job with you. Properties of logarithms. These really important in calculus and with derivatives, and a lot with the AP exam and some of the little treachery they'll throw at you. Log property 1 states that log base b of x plus log base b of y is equal to the log base b of x times y. I can go through the properties. There's 3 of them I want to go over with you, but I think what I want to do is kind of help you understand them a little better. So to understand the properties of logs, I want to go over the properties of exponents. Why? Again, we talked about logarithms represent exponents. Logs are exponents. So I'm going to go over the ones that I'm pretty sure you know a lot better, and I think it'll help you to clarify what the log properties are really saying. So if you go back to your algebra, you probably learned that when I have an x to the power m times an x to the power n, that gives you x to the power m plus n. In other words, when I multiply two quantities with like bases, I add the exponents. Again, multiplying two quantities with the like bases means you add the exponents. That's basically the idea over here. When I see log base b of x, I say, well, that's an exponent. Plus log by. That's an exponent. So basically on this left side, what am I doing? I'm adding two exponents. When do I add exponents? When I have two quantities with a like base being multiplied. Logarithmic property 2. Log base b of x minus log base b of y equals log base b x over y. Again, all ties back to your properties of exponents. When I have the base x raised to the power m divided by that same x raised to the power n, I get x to the power m minus n, or in other words, when you're dividing two quantities with like bases, you subtract the exponents. Taking us back here, log base b of x is an exponent. Log base b of y is an exponent. What am I doing? I'm subtracting two exponents. When does that occur? When I have a like base of two quantities being divided. Third log property I want to go over is this one. It says log with a base of b x to the power n. It says that is equal to n times log base b of x. Again, take it to properties of exponents. I think it'll help to clarify this a little bit better. So we know when we multiply like bases, we add exponents. When we divide like bases, we subtract exponents. Here, when I have a base and I take a power and raise it to another power, so a power to a power, you end up multiplying the powers. That's the genesis for what we got going on here. So here I have a log base b of x. This right here is a power. This n is also a power. So what I have is a power raised to a power, much like I do here. A power raised to a power, which means I multiply the two powers. The power n times the power of the exponent log base bx. Let's use those. I think a little practice will help you kind of understand them a little bit. So I'm going to take the natural log expression here, ln of the quantity x cubed times cosine x over the square root of x plus 8. Now, again, I'm doing this with the idea of, my calculus course in mind here. If I asked them to derive something like this, they would go absolutely berserk and say how awful it is and say, you've got a product rule, a quotient rule, a chain rule, and my God, you have the transcendental function ln in there too. How awful, Well, the ln is actually what makes it workable. So I'm not looking to teach you the calculus behind it, just showing you how I can reduce this, because deriving this thing would be just remarkably unpleasant. But using the log properties, I actually can convert it or rewrite it in a form or re-express it in a form that will make it a lot easier to derive. So, again, I'm going to start off using my log properties. I have a natural log, which is the log with a base of e. All three quantities have that same base of e. So I'm multiplying. So when do I multiply? When I multiply, I add powers. Here I divide, which is the same as when you subtract powers. I took the liberty of taking square root of x, or 8 plus x, and writing as the 1/2 power. Lastly, you can use our third property, in which you have a power raised to a power. Likewise here, the power ln raised to the power, and you just multiply the powers. If, in fact, let's say this were a calculus question, and I had this expression without the ln. So let's say it said y equals quantity x cubed times cosine x over square root of 8 plus x. The first thing I do would be to take the natural log of both sides, because having that natural log is the thing that makes it workable. And you say, well, how would that work out? Basically, if you said y equals the x cubed times cosine x over root 8 plus x and took the natural log of both sides, you could use your log properties to simplify it down to here, which is very easy to take the derivative of. And on the other side, you'd have the derivative of ln of y. If you know implicit differentiation, it's not that bad. So it would make it workable. Thank you for your time. I hope you enjoyed it. I hope it helped. Have a great day.